Thank you very much. Thank you. And thank you for your patience. So for now, as Claudia already announced, we will try to connect with Serg Bell. Let's see if we get him on the screen. So I
think I'm here.
Hi. Serg Bell, can you hear me?
Yes, I can hear you. Can you hear me?
Wonderful. I can hear and see you. So
that's great.
I will leave the stage to you to talk about machine intelligence in science by constructor approach. Enjoy.
Right. So this is a very general purpose speech, which we have prepared very hard over some last months, just to carry a very simple message. So the fact of the message that we're surrounded by problems. This is well known. We are very much aware of aging and disease, where aging is one of the versions of disease. We are surrounded by poverty and social injustice. Apparently, this is related to aging and disease and related to everything else. We do have generally huge problem with nature, environment, and sustainability. There's many ways to fight it, and not necessarily always very straightforward. Definitely, it is not about stopping progress. We are apparently experiencing a very difficult time with war and violence, and for sure we understand that due to many of the problems before, we need to explore universe and space. We cannot stay as a humanity on Earth. This is very clear. At some point, it will not be enough, one way or another. Now, we know that the way to solve problems, which has worked for humans very well, is science. And there is huge advances in science over the past 100 years, 150 years specifically. But we still have many unresolved problems in science. Very basic problems, they are in physics, such as, why do we have so much dark matter? And what is the physics of it? Finally, unified theory between gravitation and quantum mechanics, which is potentially related to interpretations of quantum mechanics, which is related to a huge question about what is time. We don't know in physics what is time and what is scale. Scale is related to time. Things are only separated because it takes time for light to reach one thing to another. We are not completely clear of the reach of machine intelligence, whether it can be subhuman, human, or superhuman, and what can it do. We definitely do not know what is a potential reach of life. Where can life go? What is life and what is aging, and how can we age much longer? We know maybe how to age 2 times longer, but how to age 10 times longer for sure, it's not clear at all. We don't know how human brain works. It's a basic thing. It's in the head of everybody of ours, but we even have Nobel Prize winners such as Roger Penrose, who won Nobel Prize last year, who is thinking about the fact that there is non-classical interactions in the brain, and there are some research recently which is saying that brain is not just a classical computer. And also recently we started to realize that we need a theory of knowledge, that knowledge is a significant physical matter. It's part of the universe. It's not just some emerging phenomenon, and we don't really have a theory of knowledge, while knowledge does affect matter. And if you think about humans and you think about knowledge, there is very clear evolution of knowledge, which has happened over the past several billion years, started from basic organisms such as bacteria, which invented the knowledge copying knowledge preservation and knowledge generation mechanism, DNA, which then resulted in more complicated behaviors and basic nervous systems of things like reptiles and other invertebrates, which then led to even more sophisticated social behaviors with some version of maybe cultural behaviors transferred from generation to generation in higher animals, for example, such as wolves. And then we came to learning and memes, which are present and primates and aping and copying each other. And there are some signs of language, but then we get into humans. And today we can think of humans as a universal explainers. Humans are able to create, record, preserve, transfer explanatory knowledge. And so, you know, it is a big question which we don't know the answer is whether humans are universal explainers and can explain the universe at all or not. Now, if we look at human brain, which is much younger than the life species, it went through significant evolution over the past millions of years. But even with human brain, we have many things which we don't understand. So the basic thing is compute, memory, and communication. We definitely know that there is a different speed, different memory capacity, and different learning and communication capacity of different people's brains, but we don't necessarily know how to manage it, how to improve it, what causes one brain to work much better than another brain. It sounds very basic, but it's a fact. We have many people in this room who have more memories than other people, but we don't know exactly why it is. The brain looks very similar if you sort of take it out and cut it out. Then you have these four interesting phenomena, which are almost philosophical at our current level of understanding. Consciousness, what is it? You know, it's clearly that it's present, but it sort of disappears in our sleep, and it sort of completely disappears with us dying, and it can be somehow restored if we are quickly enough brought to life, or part of it gets lost. Free will, which is almost a physics problem. It's almost a physics problem because it relates to the fact whether the world is deterministic. Do we have free will or not? Then we have something which is sort of intermediate between free will and creativity, which is intuition, which is ability to sort of feel certain things, and then apparently the things are correct. And you know, on a very large data set, humans can somehow come up with intuitive predictions, which in many cases end up being true, even though we don't always we are not always able to explain how. We have some ideas about intuition, but it's definitely difficult to have any kind of analogy of intuition in modern computers. And finally, we have creativity, which is, of course, related to consciousness, free will, and intuition, but we also don't know how it works. You know, clearly, most of creativity, most of knowledge creation happens in our brain, and clearly creativity is needed for almost every brain activity, because without creativity, we cannot even communicate. All of us recreate the meaning of communication in our brain, but we don't know what it is. Now, on top of that, and recently we realized that there is significant advantage which machines can bring us, especially with advance of machine intelligence, but even before with computational methods. And with machine intelligence, it is very clear that there are some you know, very specific advantages where machine intelligence can do differently better from human brains. Not necessarily better in everything, because we don't know many things on the previous slide, but definitely it is much faster. So it's 1 billion times faster in a digital computer. If we think about photonic computers of the future, we can be 1 billion times faster per operation. So much faster. It is a much larger memory capacity. So the brain apparently accumulates in some very imperfect way 2.5 petabytes of information, a lot of information. Today, to have the same amount of information in similarly accessible form, you need a, you know, a rack a sort of a cabinet of computers. But definitely today, global accessible internet information is about 100 zettabytes, 50 million times more than you have in a human brain, and that amount will grow more than 10x over the next 10 years, and will continue to grow perhaps even faster in the future. It's also much faster communication, so you can definitely communicate with a computer today. We are looking at the startups which can make a single optical fiber communicating 30 terabytes per second. So that will take just 100 seconds to communicate the full capacity of a human brain. Then you can have many more elements in a computer. A single Cerebras chip, which is the largest chip available today, has about 30 trillion transistors and only 86 billion neurons on the average in the brain. Of course, the single neuron is not a single transistor, but we already have neural networks with more neurons than a human brain. So these are objectively things which enhance human capacity. In addition to that, we're coming into the situation where we are getting very new computing paradigms, such as quantum computers. And so we personally, as a group, predict that we will have 1 million logical qubits quantum computers in the less than 10 years or around that time. And that allows to do operations which are impossible on a classical computer. So that may mean that for sure, there are things which we can explore with machine intelligence, just like we can explore with microscopes and telescopes and planes and ships, much broader and wider than we can do with human brain. Now we can see that there is a lot of confirmations to these statements. So just over the last 3 years, and specifically over the last 1 year, we see basically machine intelligence winning in every game possible. So winning in Go, in chess, in learning faster, being more creative, creating more sophisticated combinations in any game with rules. We also see good research for code. There is a lot of progress in generating code with computers, and there is a lot of code which can be generated faster than humans. One of the major problems today in overall technology, as you will hear from a speech of my partner, Stanislav Protasov, is creation of new software. And also machine intelligence can generate art, and art looks great. And in fact, in many cases, it's very difficult to see that the art generated by AI is less sophisticated than the art generated by people. AI wins, of course, different STEM competitions and solving problems in a very, very sophisticated fashion. It was solving problems. The computers were solving problems in many cases better even before AI with computational engines and computational theorem proofs. And we have also sophisticated use of AI in protein folding. Perhaps not all of the proteins can be folded well with AI, but it is much better than human intuition about which molecules to use for which drugs or which treatments. And so with that, we have one sort of major opportunity, and in the same way we do have a major challenge, and that's a challenge which we want to present to the audience and overall. So first, we definitely see that there is still many advances needed in hardware to reasonably emulate what we know today of things like human brain to be creative. These advances are happening: GPUs, TPUs, NPUs, neuromorphic processors, but there is much more opportunity for better hardware. Hardware is definitely needed. You will see that today machine intelligence researchers can easily occupy $1 billion of hardware. We recently had a proposal to create Institute of Advanced Studies for Machine Intelligence for Constructor University. And in this proposal, we, small university, need to buy almost $50 million worth of hardware and just to make sort of basic machine intelligence research. There is a lot of progress in software. There is many middleware which is created for running on that hardware. Much of it is open source. Some of that is closed source. Middleware is becoming more powerful, more sophisticated. There is many things which can be created in computers. There is much more user experience improvements as well. So you have barrier. You have many different technologies to make it easier to program, to make it easier to express machine intelligence problems, such as Julia, which is specifically targeting scientific audience, and MATLAB as a programming language. And there are many islands where machine intelligence is already used in science, such as breast research, such as cardiovascular research, lung, brain. These are just islands in medical imaging, but there are islands in every piece of science where machine intelligence is already generating significant advances. These are just islands. But there is a need, we believe, for making machine intelligence to be able to be doing science, to be able to be coming up with explanatory knowledge, which is a version of knowledge, and knowledge is a version of information, which is much more valuable, which is able to replicate itself much better, much faster, and modify itself faster. And we believe for that, there is a need for universal machine formalism. It's a way in which we can explain all of the science to machines. Machines are not humans. They don't think the same way, and they don't communicate in the same way, and don't memorize things in the same way, and don't copy things in the same way. And so talking to them in English is not necessarily great. Writing pictures is not necessarily great. Using some simple mathematics language is not great. And even programming in Python is not an ideal way to talk to them about science. And so that is sort of a call. We believe there is a need for a way to explain science of many domains to machines. And at that point, I will pass this to my colleague and partner, Andrey Ustyuzhanin, who will talk about some scientific ideas in that regard. Andrey.
So good day, good morning, everyone. Sergey, thank you for passing this to me. And so in my part, I would like to, do you think it works? I think it won't, because control is on his side. So I just use, so it's natural language recognition in process.
In a
so
human brain, yeah, I will be able to recognize what you say.
Okay. So in my part, I would like to cover two big islands, or two big theories that are out there for quite a long period of time. Due to the short time frame, it's not going to be really explanatory. So, but I hope that you will get a glimpse of the iceberg, like what kind of problems you can try to solve with this. And so, of course, machine intelligence is taking over the science, and many examples have been shown by Serg already. However, there are still no coherent and common understanding how machine intelligence actually does this. So there is no theory of deep learning that has been accepted by community. Several approaches already there, and you can switch to the next slide if possible. So the several approaches are based on the statistical physics, informational theory, representation group flow, category theory, or topos. And what I highlighted here, or that are put in bold font, is something that relies on so-called category theory. And So in the next following few slides, I'm going to give you a very short flavor or very brief flavor how it actually works and why it might be relevant to the task of building machine intelligence models that can understand something deeper that we can now. So starting from the very basic understanding, category theory is a study of the compositional structures. So you have a very simple example here. Like we start from the very basic stuff, and there are objects that somehow connected with each other within the category. So you see the category contains people, contains other people, and contains some kind of food that they like, and there are relations. So unlike the set theory that studies properties, these relations actually impose a structure on the objects that we study. And this is very important from many perspectives that we'll see. So the important thing that we can consider theory on many, category theory on many levels. And categories has already been applied to many domains. So we'll show examples where they already been successfully used. So on the next slide, I'll show you even simpler building blocks, like what category is and how you can represent it. First of all is objects, right? So that describes what kind of stuff is there. And it's not necessarily a set, it can be something bigger. Then morphisms, and those morphisms actually should be, it's not anything, it's something that allows composition. So if you draw a line connecting two dots and there is a third dot then connected with the second, then it means that you can get the first and the third using the composition of the first steps, like on the last slide. And you can display it in the two different ways. The first one, the point is an object, and the arrow is a morphism, or you can display it a little differently. So we'll see both, and those are basically interchangeable. In some examples, the second is more appropriate because it allows you to do so-called graphical calculus. So next slide, or next part of the slide. And this example of the so-called partial order category. So it has integers, and there is a relation, less of that, or more of that between any two integers. So you see some structure between those objects. So next slide, a few more examples. So a category of sets that contains sets as objects, all possible sets, and functions between sets as morphisms. So you can describe it. Or computational category. So it contains as objects all data types, and the transmorphism between data types is just some functions that do some execution, and you can compose those functions into steps that or give you a program. So and you can go on. So you can describe in a similar way almost any domain that you can think of. Right, so let's go to the next slide. But there is more, because when you think of a category as an object, right, so you kind of go to the next level. So you can describe morphism between categories, and this is a special kind of relations. It's kind of a metastructure that is described by functors. So the functors map you one category to another, and there is one more thing. If you build two functors that map from one category to another category, like on this plot, C and D are two different categories, and those functors do something differently, like but they're preserving some basic rules. So there is a natural relation between the images of objects that you put from one category to another. Like here you see FA and GA. Two different images of A. And there is a relation between those, right? So, and there is a relation between relations. So like f of f and g of f, f small and gf small are different relations that come from this new domain. So this relation is called natural transformation. So between images of the same thing in the target category. And this was the whole idea why category theory has been started. So to make able to do this meta transformation, meta step, and of course you can repeat it as many times as you want. Like it's a very, very flexible framework. So let's go to the next slide. One special case of the categories that you can encounter in many, many, many domains is called monoid. So what is it? Monoid is essentially a special kind of category that takes two objects and produces something in the same domain, producing the same kind of objects, like two colors. If you combine two colors, you get a third color, right? So like on the first part of this picture, and you just imply that the composition is associative and there is identity. So associative is demonstrated here at the center, and identity is like white color, doesn't change color at all. So combination of two objects is called a tensor product, like this circle with cross in the middle. So we'll see it on the next slide with more examples. So, and with this monoid category that actually allows you to combine two different objects into some kind of procedure, allows you to describe processes, allows you to describe topological structures, allows you to describe chemical processes, and there is so-called part of the category theory that is called resource theory that allows you to describe chemical reactions, biological processes, and many, many, many different stuff that, for example, transforms one stuff to another stuff using some catalysis, for example. And even some evolutionary biology can be described with the help of this framework as well. So trying to answer a question why tigers have stripes and lions do not have stripes, you might wonder, well, maybe it's something in the structure of a lion that you need to take into account. Like you take a knife, you dissect lion and tiger and look, but you don't see any properties that correspond to the stripes. And then you take a better knife and you go repeat this procedure until you come up with a DNA, and you say, aha, maybe this is the reason why something is different for one cat and for another cat is different. But probably it's not the best answer. It doesn't answer why it is so. So next slide shows you the one backend. So the composition on the bottom of the slide show you actually how the neo-Darwinian theory actually explains this reason. So because the lions and tigers have to hunt in different environments, and during the adaptation process and taking into account properties of environment, you actually develop some features that give you a better advantage in the survival process. So, and you can describe it as a simple functor or simple morphism that takes a product of different components. So on the next slide, there is a Rosetta Stone table that shows the relation between different fields that already has been described using category theory formalism. It's not like the full description of physics, full description of topology, logic, and computation, but at least some part of those you can describe with a category theory. So the next slide shows very important theorem that is modestly called lemma in category theory. You need a lemma. So it's fundamental understanding that if you have two objects, so those could be quite complicated in the nature, but you can somehow embed those into a category of sets right? And or whatever you mean. So you can compare those objects not by comparing all the details of those objects, but you're comparing relations of those objects with everybody around, with all other objects, potentially. So, and if those list of relations is the same for two objects, you can conclude that those objects are the same as well. And we see many examples how this actually works. So many theorems has been proven using this lemma in the field of mathematics, in topology, in homotopy, cohomology, etc. But in even real life, like in physics, you can describe the properties of material or compare materials using spectrums, right? So if spectrum are matching with each other, the complex structure of a material is actually the same. And psychology, when you don't know how the mind of people works and what's inside, but behaviorism says, okay, let's look at the behavior of people, and if they're behaving similarly, they're thinking in a similar way. Or in linguistics, the quote by John Thorth is, "You shall know a word by a company it keeps." So on the next slide, I provided a few examples that uses already the formalism of category theory, like game theory. It uses category of so-called lens. So it shows connection or morphisms depicted by boxes that run in one direction and answers going to another directions. So on the next slide, that very similar formalism has been applied to describe the gradient descent or backpropagation that is used in the many supervised learning neural network nowadays. So those are on the left backpropagation lens structure that is used for training a neural network, and the same formalism is actually shows how you can adapt the architecture of a neural network to perform a better with better accuracy. So it's meta-learning structure. On the next slide, it shows how category theory used in completely different domains. So it is like the whole field of physics, like it's called topological quantum field theory, that describes the property of matter that remain within a very low energy boundary, very low energy, and you transform properties, change the property of matter, changing relative positions between objects, between particles. Like those are modeled the vortices of anyons, and you change configuration by rotating those particles around each other that you can describe in a similar way. You can see this on the right part of the slide, moving one particle around another. So, and it was quite exciting field of research. The whole physics was built on this, and the next slide shows just how you can design. So it's conceptual idea how can design computing process using this property. And the interesting fact that you can describe this computational process using categories of those like braids that twist around each other. So computational process effectively is described in the category of using category of topological transformations. And recently there was a proof given by the team and published in Science. If you're interested, you can follow the link that shows that this actually approach can actually works. So next slide shows a little bit different. And here is the references that you might find interesting and give you some breadth of the fields that are covered by category theory. Next part of this slide shows books by Bob Koke, Alex Kissinger, about thinking in pictures and describing quantum physics in pictures and categories, and the course that recently published by DeepMind that binds together category theory and deep learning. So this was pretty much about category theory, what I wanted to cover. Next slide goes into a little bit different domain, but is somehow related. We'll see a little bit down the stream how this theory, it's a different theory, that actually tries to approach studying physics from a little bit different perspective. Instead of trying to figure what are dynamic laws are given for the system under consideration, it tries to ask a question, what are the possible laws actually that can happen under the object that we study, for the object that we study. So, for example, if we study a motion of a solar system, planets in the solar system, it can account for Newton laws, or it can account for general relativity laws, for example. But reasoning that happens in this theory starts with the constraints that are called principles, right? So, and those principles actually guide selection of laws or kinds of laws that can happen in given world and given system. Another thing that they take into account, what is impossible, they call it counterfactual. And there are several like foundations for different theories that, for example, bridge quantum classical worlds of information, probability, thermodynamics, life, etc. So, and even they suggested experiment that can prove if the quantum theory can express, gravity theory can express quantum properties, just coming from the ideas of constructors. One property one feature this theory gives is how you can prove irreversibility of certain kind of systems. So they take into account not the controversy between or asymmetry between macroscopic and microscopic things, but they say, okay, maybe there is a constructor, some kind of device or machine that can perform certain tasks with great accuracy over and over again, and if it can indeed be constructed, then the process can go in one direction, but if it's not, can go in another direction, so the same constructor cannot go into the opposite direction, then maybe this process is irreversible. So, and they managed to show how this approach can show irreversibility of extraction of work or thermodynamic system and quantum reversibility of certain processes. So this was like a very basic foundation, and here is what I wanted to show. The most important thing in this roller coaster of theories that definitely if we want to make foundation for something that would be applicable to different domains and bridge the gap between the machine intelligence algorithms and what humans actually can expect from those algorithms, it should be based on math because math is a universal language, universal tools that matches similarities between different branches of science and tries to extract those patterns into something useful. And there are brilliant developments based on math in category theory, constructor theory, that I guess will be helpful, and I encourage you to take further look into how it can be applied to your domain. And if you have questions, I'd be more than happy to answer during those. I guess so it's not the end. I now pass the word back to Sergey. Sergey.
Yeah, okay. I will be very quick. So first of all, I just want to summarize a little bit what we are trying to say with Andrey. We're trying to say that we believe that machines can play not just the role of calculators, of sophisticated calculators, but they can come up with new explanatory theories. I would not be surprised if unified field theory, which is a holy grail of physics for the past 100 years, unifying gravity and quantum mechanics, will be either made with the help of machine intelligence or will be made by machine intelligence. Second, I want to switch gears and very quickly go through our change, which might be not unnoticed. We have renamed this particular institution to Constructor University. We have renamed our overall effort to Constructor Group. And I want to point out that this is not directly related to constructor theory. Constructor word usage is very broad. Of course, most famous is Universal Constructor by von Neumann, self-replicating machine, extension of what is Turing machine, which is a computer which can emulate any digital computation, universal Turing machine, any physical computation, but cannot replicate itself. There is constructivism in philosophy. There is, of course, constructor theory, which is a concept, very interesting concept. It's just a concept, but it's interesting, and it's very easy to understand, and it allows to understand some things such as quantum mechanics easier. There is construction in programming, constructivism in education. There is more example where you can think about constructors in chemistry. Catalyst is effectively a constructor, something which is causing transformations. The ultimate constructor is DNA. You can reconstruct, Andrey Ustyuzhanin, despite the complexity of his speech, with the usage of his DNA. He is, simplified to a DNA, but his speech will not be contained in it. There is constructors which construct most sophisticated things which humans have done to date in terms of machines, which is airspace programs. We're not yet on Mars as humans, but will soon be, as it's promised by SpaceX, for example. There is constructors in Formula One. It's good to be constructive. For example, we approached the problem with Zoom constructively, and we were able to speak a little bit later today. There is many constructor words applied to education, business, psychology. It's applied to social science. And in fact, the ultimate criticism which we received when we chose this brand, construction worker, is not a bad word. It's not a curse. When you build a university or you build a scientific institution, you do need to make and construct buildings, which is one of the main assets of the universities and research centers, and you need to build large machinery. And perhaps the first example of human society is large constructions like pyramids of Egyptians. One of the things we want to do in Constructor University and Constructor Group is to make new constructors, people who are ready to design, engineer, research, develop a future. And there is these examples of famous constructors making a huge change to our world, or making a huge brands to themselves. Leonardo da Vinci called himself a constructor. These space programs, helicopters, which all of us use. The most famous constructor in Red Bull, a person who repetitively were able to win in 3 different teams, Williams, McLaren, and Red Bull, very different conditions. And, of course, there is many constructors in science. It's not working. So, one of them is the ultimate construction of living organisms, basically evolution of selfish genes, which ended up bringing humans alive. And then there are the scientists, Seymour Papert, constructivism and theory of learning, Jack Welch, effectively creating a repeatable process of building businesses, constructive approach to chemistry. First, way before quantum mechanics and nuclear physics, by Dmitry Mendeleev and Mendeleev table, which is sort of a knowledge to construct your ideas about the chemistry. Constructivism in social sciences. Apparently, you can think about humans as automatas, and you can predict their behaviors using cybernetics. And of course, there is much of the same in psychology. You can think about psychology, not just sociology, in constructive way. And so we basically decided in that respect to change our brand. And it's not directly related to the concept of our speech, but it's related to what we're planning to do. First of all, we had to change it. And it had to be a single name: Constructor Group, Constructor University. Any university can be called by a person. We don't have that person yet, at least. None of us is dead yet, and even when dead, not necessarily a good place to be called by a human. Human, it's sort of like calling yourself by a certain DNA sequence. It's not that important part. Calling yourself by a city is also strange. We're living in the universe. Most of institutions today are global, and so it's better to use a concept. For constructor, there is this dictionary definitions: a person or thing that builds, a person or company engaged in construction business, and person or company which builds things, cars and aircrafts, but effectively a person and thing that builds. And our definition of constructor is an object that can perform a task, transforming the system from state A to state B many times and changes insignificantly in the process. Apparently there is very few things which don't change at all in the process, but insignificantly is good enough definition. It's it allows to make another transformation of the same kind. Constructor could act on very complex systems, such as people groups, devices, can be made of other constructors and can build other constructors. That's our definition. Again, there is an intersection between mathematical category theory, which is one of the most fashionable fields of mathematics today. A lot of young mathematicians study it. It's a most abstract view of mathematics and other fields. And so it can be applied to university. And with that, just reminding everybody, we here believe that universe is a computer, and that relates to every part of human activity. That's for sure relates to chemistry and physics and mathematics, but it also relates to biology and medicine, and it also relates to social science and psychology and political science. It actually also relates to history, the way we study it, and anthropology. And so it can all be simulated on the computer. And today we have this wonderful system which is called cloud, where whatever we invent as a computer can be immediately connected to the cloud and we can access it. And today on the cloud, we already have GPU, CPU, TPU, and probably we have somewhere memory star arrays, photonics, and we have some form of quantum computers. And if we make some more sophisticated computers, we can definitely connect it. And all of that is enhanced by many humans who make it better, even though it's supposed to learn itself. In many cases, machine intelligence learns with humans. And the improvement of computers is the future of improvement of humanity. It's as much important to improve computers, improve computational methods, improve machine intelligence, learn more about mathematics and physics as it is to go to Mars and go to stars. And for that, you need advanced materials, hardware, software. It means that there is a lot of opportunity for new businesses. And up until we figure out what is consciousness, intuition, free will, and creativity, it requires people. We still are much far away from exploring the potential of humanity. And for that, we're building what we're building, which is effectively this things, Constructor University, focused on computer physics, life sciences, businesses, and social sciences in interdisciplinary way, and always applying computational methods and machine intelligence to all these areas. And four businesses on the right: Constructor Rollers, which is machine intelligence platform for science and research; Alimira, which is computing and application platform for learning and education administration; and 2 investment vehicles which we use to invest. And with that, we want to invite any of the listeners to participate, help, be sponsor, partner, invest, use our services as education services, join us. We're constantly looking for people. Today, we have about 750 people, notably 1 year ago, we had less than 150 people, and 3 years ago, we had no people. So we're growing very fast in terms of number of employees, but we will probably grow more than 10x in the less than 10 years in terms of number of people. We are also looking for students. There is a lot of things to do in science. You can do a lot of things in computing. Computing is a fundamental science, and it's very early. There is much more to do, how to emulate the universe in computers using advanced computers. You can do a lot in physics. Physics is full of unknowns, more unknowns in the last 10 years than in the last 100. You can also, if you are fast enough, get a Fields Medal. You can only get it if you are less than 40 years old, so you should rush and join us early. In a private university, will be welcome young students. You will have more chances getting it if you are 16. Bring us your startup. We are very happy to help you to get to a 1 million, 10 million, 100 million in revenue, 1 million, 10 million, 100 million, billion in funding. And of course, we invite you to use Rollers and Alimera. These are real products. We use them in Constructor University, but we definitely build them mostly 99.9% for external scientists, educators, and administrators. Thank you very much.
Thank you so very much, Serg Bell. Please stay with us for a second, because we are very happy to announce we just received some exciting news. Since we opened the conference, 1,000 guests from all over the world, they joined us via Facebook, LinkedIn, YouTube. That is absolutely amazing. So are we still on with Serg Bell? Can you still hear us?
Yes, I'm
yeah,
definitely
okay, perfect,
here.
perfect. And this audience is hungry for knowledge, and many questions arrived, and we have the capacity to ask one of those questions. So, Serg, this one is for you. Can you tell a bit more about your vision on knowledge and cross-disciplinary approach?
I think one thing which indirectly alluded could be alluded from the speech of Andrey is that we believe that this division to disciplines in science is very artificial. So there is this borderline between politics and history and psychology and biology and medicine and chemistry and physics and mathematics and computer science is very artificial. All of this are related, and all of this are explored in a similar fashion. And so, I'm not sure what to answer in terms of vision, but for sure the future is interdisciplinary, and for sure we are at the very beginning of understanding and being able to construct the universe, and that is, interestingly enough, not just universe for humans, but universe for living species, and not just universe for human and living species, but the overall universe. There is no reason to believe that the reach of knowledge is any less than the reach of life, and that is any less than the reach of matter. And so the reach of knowledge, potentially is much more broad. But again, I'm not sure how to answer this question. The vision is never give up, keep on it, keep researching, keep talking, keep exploring different ideas, and stay open for more.
Thank you very much. Ladies and gentlemen, Serg Bell.